So here we go in chapter 18. Chapter 18 is our second chapter on thermodynamics. Last semester we did a chapter on thermodynamics where we dealt just with delta H, the enthalpy. Those are bond energy changes. So we took a reaction and calculated the changes in bond energy that occurred. That's enthalpy, delta H. Remember delta H of products minus reactants, and we had Hess's law that we threw in with all that sort of stuff. Now we come back to it again after we've had some experience with equilibrium and kinetics, and we're going to re-look at thermodynamics. We're going to start with delta H again, kind of remind ourselves of what that does. And if you remember last semester, I was very careful when we decided whether something was endothermic or exothermic, and then we decided is it spontaneous or not. We were making a guess. We were guessing spontaneous for things that were exothermic and guessing non-spontaneous for things that were endothermic when we had to decide. But we had to guess. In chapter 18, with our new look at thermodynamics, we'll know for sure whether something's endothermic or exothermic. It's not just based on enthalpy. There's also some other things that feed into it. So we're going to take one quick look, one quick review of enthalpy. So back last semester, we had reactions like 2 C4H10s plus 13 O2s. I'm leaving all the states out so they don't clog up the things on your screen. Makes 8 CO2s plus 10 H2Os. All of this is in the gas phase. And so when we looked up all the values in the back of the book, remember the big table in the back of the book, we had to look up the enthalpy of C4H10, O2, CO2, and H2O. Enthalpy of formation of all the elements was 0, remember? So sodium as a solid would be 0. Copper as a solid would be 0. O2 as a gas is 0. Bromine as a liquid would be 0. So if it's in its natural state at room temperature, it's 0. So going back to that table in the back of the book, we're going to look up the delta H of formation in kilojoules per mole for each substance. So for C4H10, it was minus 126. O2 is an element, that's 0. CO2 minus 393.5. And H2O as a gas, these are all gas phases. As a gas, minus 241.8. Again, make sure you know what state things are. I told you everything here is in the gas phase, just so we have to write all the little gas designations after each one. When you work a problem, make sure you know the state, because water as a gas and water as a liquid will be in the table. CO2 is a gas, and maybe even CO2 as a solid might be in the table. And so make sure you know the physical state that they're in so you get the right delta H value. And so the delta H of formation for the reaction. So we usually write that as delta H 0 for standard conditions. 0 degrees C, 1 molar everything, 1 atmosphere pressure of everything. Delta H for the reaction is the sum of the delta H of formation of the products minus the sum of the delta H of reaction for the reactants. So it's just product numbers minus reactant numbers. We have to account for the coefficients in the equation, right? So when we set this up, delta H for the reaction, we go to the product side first. It's 8 times minus 393.5 plus 10 times minus 241.8. Those are all of our products minus our reactants. So minus 2 times minus 126 plus 13 times 0 because it's O2 kilojoules per mole. So then it's time to grab your calculator. And back in that chapter last semester, this was troublesome for a lot of you. Making sure you get everything's signed correct when you plug everything in. And there's several different ways you can do it. You can do it left to right. You can do this side first because it's being subtracted, or however you like to do it. I'm going to work one left to right. So follow along with me just working it left to right. I have 8 times 393.5, flip the sign, equals, right now it's minus 3148 on my screen, minus 10 times 241.8 equals, let me try that one more time, 8 times 393.5 minus equals minus 3148 minus 10 times 241.8 minus 5566 for what's on the left-hand part of the equation. Now when I go through here, I know that the sign flips for everything. So I take my minus 5566 and add 2 times 126. I don't have to do anything for that term. So delta H of reaction for this process is minus 5314 kilojoules per mole. That unit can also be troublesome. There were some issues last semester with folks not quite recognizing what that always meant. It's kilojoules per mole of balanced equation. So 5,314 kilojoules of energy are released, because it's negative, for every 2 moles of C4H10, 13 moles of O2 that are used, 8 moles of CO2 that are produced, or 10 moles of H2O that are produced. So there was usually a follow-up on this, where we had to calculate delta H for the reaction, and then if we had so many grams of one of the things, how much energy changed hands. This is a participant in the reaction. This much per 10 H2Os, this much per 8 CO2s, 13 O2s, or 2 C4H10s, okay? So we'll come back in the next video, we'll take this answer and we're gonna work with it and see how much energy got released in terms of enthalpy due to this reaction. Stay tuned.